Haack, closed string, disk amplitudes in the pure spinor formalism. You have 40, let me see. Yes, you have 40 minutes.
Okay, thank you very much. Thanks a lot, everybody, for joining on a Sunday evening. Let me just start the full screen mode. Okay, can you see the screen?
Yes, we see the screen. Perfect.
Okay, great. And you can also see the mouse, I hope. Yeah, so let me also thank the organizers, in particular George Tsoupanos, for inviting me numerous times in the past already. And for one or the other reason, I could never accept his kind invitation. And finally now, due to Corona, I can join, if only virtually. I hope at some point I can come also in person. I'm presenting work here in collaboration with Andreas Bischoff from last year. He was master student at that time, and I'm actually presenting his master thesis work. And now he is PhD student, at the Max Planck Institute in Munich. One second. Yeah. Okay, here's an overview. I will start with some motivation, review the pure spinor formalism, because I don't assume that many of you are familiar with it. Then I'll adapt it to closed string disk amplitudes and present some application to 2- and 1-point functions. Let me start with some motivation about why disk amplitudes. Well, they give the first and thus most important quantum corrections to the sphere level in string theory. And one particular motivation for myself concerning disk amplitudes is a question about higher derivative corrections to the dBi action. And for example, this particular term here, which is a quartic term in the Riemann tensor. So the R stands for the Riemann tensor, not for the Ricci scalar. It's a schematic way of writing it. The epsilon 10 is a 10-dimensional epsilon tensor, and all the indices appearing here have to be contracted in some way. We don't really need to be more precise. And the e to the minus phi, the e to the minus a dilaton tells us that this would be a disk contribution. So let me be a bit more precise about this. So concerning type 2, it's known that there are two kinds of R to the 4 terms. There's this one that I just mentioned, and then there's another one involving this T8 tensor, which has 8 indices. And again, all these indices of the T8 tensors and the Riemann tensors have to be contracted. And in the type 2 theory, both of these structures arise both at the sphere level, so e to the minus 2 times the dilaton. They arise at the sphere level and the torus level. Yeah, and for type 2b, these terms are also inherited by type 1 after the Orienti folding. It's known by the work of these authors that this kind of structure of R to the 4 terms leads to corrections to the 4-dimensional kinetic terms in a compactification to 4 dimensions on a manifold with non-vanishing Euler number. And this structure of R to the 4 terms leads to a correction to the 4-dimensional Einstein-Hilbert term. So for the heterotic string, it also contains these two types of R to the 4 terms, but the difference to type 2 and thus also to type 1 is that this epsilon 10 term only arises at sphere level, not at the torus, the loop level. And this poses a problem or a puzzle. Yeah, in type 1, this term arises at 2 orders in the perturbation theory at least. It inherits these 2 orders from type 2b. And in the heterotic theory, there's only 1 order in perturbation theory where this term arises. So how can this be compatible with heterotic type 1 duality, this strong-weak coupling duality? And this is, of course, not a new question. It was addressed by several people in the past, but I think there's a very interesting recent proposal concerning this. given by Green and Rodra. And their suggestion is they write the out of the four terms in the heterotic theory in terms of two superinvariants, ten-dimensional superinvariants, which contain as these bosonic, among the bosonic terms, these R to the four terms, the J0 in this combination. And then the I2 only contains the epsilon 10 term. And they suggest that one of these superinvariants, the J0, appears with a particular coefficient. An Eisenstein series, which has such an expansion, has two perturbative contributions and then non-perturbative contributions. And if you take this dilaton dependence with this explicit prefactor here, you get the e to the minus 2 phi from the sphere level. And this one, if you take that one, it cancels this. So this is a torus contribution in the heterotic string. But it's multiplying with both of these structures of the R to the 4 term. I told you that this one, the one with epsilon 10, in the heterotic string only arises at sphere level. So in order for this to make sense, you have to subtract it explicitly again. That's done by this term. So how does this help for this question of heterotic type 1 duality, expressing things now in this in these superinvariants? Well, this coefficient here, if it's really the full Eisenstein series, this is an S-duality invariant. And if you then also look at how these terms transform under this transformation, you will see that these terms by themselves, they are just invariant. They map invariantly to the type 1 theory, which means, as we just discussed, this describes the tree level and one loop contribution on type 1 theory. That's what you want, yeah, that's what you inherit from type 2b. But then there's also this piece, and this then has to be mapped separately, and that's mapped to something which has a dilaton dependence of a disk level. So in other words, Green and Rodra indirectly using heterotic type 1 duality predict such a term at the disk level or projective plane. Yeah, I mean, you just see the dependence on the dilaton. It could either come from the disk or projective plane, or probably from both. If you want to check this directly, then this would require a 5-point graviton amplitude on the disk or projective plane. This is obviously a very daunting task, but I would think that it might be possible to check the presence of such a term indirectly. If you take type 1, if this term is there on the world volume of the D-branes and O9 planes, if you compactify on a Calabi-Yau with non-vanishing Euler number, you would get, as we discussed earlier, a correction to the 4-dimensional Einstein-Hilbert term, proportional to the Euler number of the compactification manifold. So maybe you can see such a term in a disk or projective plane amplitude. On the other hand, this raises again a puzzle, which is maybe mainly appreciated by the experts in the audience who are familiar with string, concrete string amplitude calculations, because a disk and projective plane, if you're scattering massless states which only have external how to say polarization, like the gravitons, which are polarized exclusively along the non-compact dimensions, it's not clear how this can feel anything about the compactification space, so how it can depend on the Euler number. This is something, if someone in the audience has some idea about this, I would be very interested to discuss this more. Okay, this is my kind of personal motivation for looking at disk amplitudes. Let me now introduce a pure spinor formalism. It's manifestly super Poincare covariant. So it's superior to over the RNS formulation, which is not manifestly supersymmetric, space-time supersymmetric. And it's superior compared to the Green-Schwarz formulation, because that is only quantizable in the light cone gauge. Moreover, it's known how to, there's a prescription how to compute loop amplitudes, even though it's more straightforward to do that in the non-minimal formulation that I'm not going to discuss today. The equivalence to the RNS formalism, as far as I know, has not been really proven in all generality, but it has been shown in many examples in all the cases where amplitudes have been calculated in both kinds of formalisms, they did agree. I should also admit that mainly in the pure spinor formalism, massless, so amplitudes of massless states were calculated, even though recently there were also some results on massive states, scattering of massive states. The pure spinor formalism can lead to simplified calculations of amplitudes, and I want to list here three, as I think, rather impressive examples of this. So, for example, Polycastro and Simpis calculated the complete quartic effective action of type 2 at sphere level, including fermions and Ramond-Ramond fields. Then Gomez and Mafra managed to calculate a 4-point string amplitude at 3 loop in type 2, even though only at low energy, so only the expansion, the leading term in an expansion for small momenta. And there's a pretty compact expression for arbitrary endpoint functions of massless open strings on the disk by Mafra, Schlotterer, and Stieberger. So now I want to give you some short review, or it's actually not so short because, as I said, I don't assume you to be familiar with the pure spinor formalism. I'll give you a review in its technicalities that will be needed later on. And I structure this in 3 parts. I first tell you something about its CFT, then about the vortex operators, which are quite different from the RNS formalism, and then the steps how to calculate correlators. So here I give you the worldsheet action for the type 2b theory in 10 flat spacetime dimensions. It's pretty simple. The kinetic term for the axis is the usual one. And then you have these all these quadratic terms. The theta alpha and theta bar alpha are the spacetime superpartners of the XM. The position of the index here tells you something about the chirality of the spinor. So these have the two, both have the same chirality, so it's type 2b theory. And the p alpha and p bar alpha are the canonically conjugate momenta. And then there are these additional spinors, lambda alpha and lambda bar alpha, and their conjugate momenta. And these are the fields which give the formalism its name, because the lambda alpha and lambda bar alpha are pure spinors. The definition I wrote down here. So a pure spinor is defined by this contraction with some Dirac gamma matrix, 10-dimensional gamma matrix. If this gives 0, then this spinor is called a pure spinor. So also the Green-Schwarz formalism makes use of these theta variables, but this action is much simpler, and the simplification arises due to an idea of Siegel to treat the conjugate momenta as independent variables. And in addition, compared to the Green-Schwarz formalism, you also have, as I said, these new degrees of freedom. One way to see that they are necessary for this action to make sense is, otherwise you wouldn't get central charge C equals 0 and C bar equals 0. So you can think about these fermionic terms, or spinorial terms, I should say. The thetas are indeed fermionic, they are anti-commuting spinors, but the lambdas are commuting wild spinors. So you can see these spinorial terms here, if you wish, as some version of a BC system that you know from the quantization of the string. For example, from the reparametrization ghosts and the super ghosts. They have a similar action, how we say, linear first order kinetic term. These BC systems, however, have lambda equals 1 in contrast to the ghost systems in string theory, which have lambda equals 2 or 3/2. And this implies that the dimension of these momenta here, all of them is, the dimensions is 1, and the dimensions of the spinors theta and lambda is 0. These are the 0-dimension spinors, fields of the theory. Also, looking at these as some BC system, you can infer the contribution to the central charge. And if these lambdas here were unconstrained, then they would just contribute exactly opposite, but in the same absolute value as these terms here to the central charge. So you have 16, if you wish, BC systems here. And that would just cancel these because these are commuting and these are anti-commuting. So you see, not all of these 16 degrees of freedom or 16 components of these spinors can be independent degrees of freedom. And it turns out if this lambda is a pure spinor, then it reduces the number of independent degrees of freedom to 11. And that's exactly what you need for vanishing central charge. In order to define the vortex operators in a moment, let me also introduce supersymmetric fields, which are kind of composite operators or fields made out of the basic fields that we saw here in the action. The pi m is given by partial xm plus these bilinears in fermions, and d alpha is based on the canonical conjugate momentum of the thetas and gets this additional composite contribution. Of course, there are also anti-holomorphic analogons to these. I usually don't write those down. The OPEs of these fields in the action are the usual ones. For the axis, I set alpha prime equals 2. And these are the usual OPEs that you are familiar with from a BC system, either anti-commuting or commuting. Another operator which will play a role when we write down the vortex operators is the Lorentz current. I just want to focus on its spinorial contribution, and mainly this contribution from the pure spinor and its momentum. The gamma mn here with 2 indices is just the anti-commutator of 2 gamma matrices. So this combination here I denote, or is denoted in the literature usually by capital N mn, and that will feature also in a moment in the vortex operators. And finally, the last ingredient in the description of the CFT is this operator Q, which is an integral over the pure spinor and this composite operator d alpha here. And this can be shown to be nilpotent, Q squared equals 0. And this also makes use of this fact that lambda is a pure spinor and of the OPE of the d alpha. So if you have 2 Qs, you have to make use of the OPE of 2 Ds. That gives you one of these Dirac matrices, and then the lambdas in the Qs, they contract with this gamma, and you obtain this condition here, or this expression here, which is 0. Yeah, so that Q squared is 0. So that you can look at the cohomology of this operator, and turns out Berkowitz showed that this coincides with a superstring spectrum. And I should say in this review of the pure spinor formalism, I don't really give so many references. Much of it is goes back to Berkowitz and collaborators. Now I come to the massless vortex operators. First, the open string. And here it's very similar to the RNS formulation. They come in 2 different versions, the unintegrated and the integrated version of the vortex operator. Whereas for the bosonic string, for example, you also have this unintegrated, integrated, and they are very similar. They basically just differ by factors of the C ghosts. Here in the pure spinor formalism, the difference between the unintegrated and the integrated vortex operators is more substantial. Also notice that there is no equivalent of a picture. So in the pure spinor formalism, yeah, this makes things also simpler compared to the RNS formulation. You don't have any pictures, you don't have any spin structures, any sum over spin structures and so on, which are needed for the INS formalism in order to obtain manifest, or not manifest, in order to obtain space-time supersymmetry. Okay, so the unintegrated vortex operator has a relatively simple structure. It contains a factor of the pure spinor. And then this A alpha, that's a superfield. And I'll give you the form on the next transparency. It only depends on x and theta. And it's a BST invariant. So acting with Q on it gives 0. And the integrated one, well, its definition is basically this. If you act with Q on it, it should give the derivative of the unintegrated one. This is also a relation you have in the INS formalism. And from this, basically, it follows this form of the integrated vortex operator. You have these dimension 1 operators here. Again, this NMN was this combination, this part of the Lorentz current. And all these 4 fields here, these are superfields describing all the same degrees of freedom, and the degrees of freedom of a massless n=1 vector multiplet, so of a vector and or gluon and gluinos. And I just give you the form here of these superfields. For vanishing fermionic degree of freedom, only a polarization of a massless gauge field, even though it's simple to generalize this to also include fermions. So the fermions are treated very similarly to the vectors and also for the closed string. Something analogous holds. That's why it's so much easier, or I mean, it's often easier to calculate amplitudes for Moore fields or fermions with this formalism. It's equally difficult or easy as for the bosons. So the psi is a polarization of the gauge field. It appears here in these brackets is always some expansion in the thetas. It goes up to theta to the 16 for these Majorana-Weyl spinors. And it always contains terms involving the momentum of the gluon and the polarization. The x only appears in the front here in these exponentials, which you also know from the vortex operators in the INS formalism. And yeah, I didn't write these higher terms. They are known, but often they are not needed for the calculations. For the closed string, I focus on those vortex operators which describe the fields which in the INS formulation would reside in the NS-NS sector. So the metric Calpramont field and dilaton. The polarization tensor is the tensor product of the polarization vectors of the corresponding open string vortex operators. And the vortex operators are the tensor product of the corresponding open string vortex operators, for the left and the right movers. I included here these indices A and B, which could be either 0 or 1, depending on whether these factors here take the form of the integrated or unintegrated vortex operators, 0 and 1 here. So usually in the calculations in the past, A and B were taken either to be both 0 or both 1, but we'll see that for closed string amplitudes on a disk, you also have to look at this kind of mixed representation where one of them is 1 and the other one is 0. We'll come back to that. And this vortex operator, this closed string vortex operator now contains from these two factors here the exponentials, which you can combine to the exponential of the full embedding field, which, as you can see here now, I view as the sum of a holomorphic and an anti-holomorphic piece. Now, the prescription how to obtain tree-level correlators, similar to the INS formulation, you have to fix a conformal killing group on a sphere. The conformal killing group is PSL2C, so you can use this leftover symmetry in order to fix 3 vertex operators, which in this formula here I took as the first one, the n minus first one, and the nth one. All the other ones still have to be integrated, so they are of this integrated type. And this is a formula for the disk amplitude, but with only open strings. I'll tell you in a moment how to modify this if you want to scatter closed strings on a disk. So for only open strings, which is what people discussed mainly in the past, the killing group is PSL2R, so this allows you to fix 3 positions of the open strings. Okay, and I'll in the following describe the prescription how to calculate tree-level correlators at this example because it's simpler. But for the closed strings, it's very similar. So the first step is that you have to integrate out all the non-zero modes via Wick's theorem. Yeah, you saw that the action is just quadratic. It's basically a free theory. You can integrate out, like you are used to doing it also in the RNS formalism, all the non-zero modes via Wick's theorem using these Green's functions here. Once you did this, you still have to take care of the zero modes of the fields, and these at tree level, and this is a huge simplification, only arise for the fields which have dimension 0. So these were the axis and also the theta variables and spinors and the pure spinors. Yeah, not their canonical momenta, which are p and d, alpha and n. So these are all dimension 1 fields. They don't have any zero modes at tree level. They do have zero modes at higher loops, and this makes calculations at higher loops more complicated. But at tree level that we are discussing today, you have to integrate out all these fields which appear in the form of the integrated vortex operators. You have to integrate them out via Wick's theorem. And once you did that, they are not there anymore in the expression for which you have to calculate the correlator. You are left with an expression which only contains zero modes then from these fields. And the zero modes of the axis you can integrate out exactly in the same way as you do in the RNS theory. It gives you a momentum delta function. And then you still have to take care of the zero modes of the theta and the lambdas. Now, once you integrated out all the other fields, you end up with an expression which depends on the 3 lambdas, which come from these fixed vortex operators, the unintegrated vortex operators. Yeah, they contain each a factor of lambda. And we have 3 of them. And then there's some expression depending on theta and, of course, the position of the vortex operators. And this is some, how to say, it has an expansion in theta. I mean, there are many different terms and they have different powers in theta. Now you have to basically integrate over the zero modes. You have to give a prescription how to perform the zero mode integral now over these remaining zero modes. And there's a zero mode prescription in the minimal pure spinor string, which, as far as I can tell, is not really derived yet from first principles, but it goes like follows. All the terms, as I told you, this is some kind of expansion in theta. And the only term that contributes, it's non-zero, is one which contains 5 powers of theta. Yeah, you have the 3 lambdas and then 5 powers of theta. This is the only term that contributes. All the other ones are set to 0 by the zero mode prescription. And this is, how to say it, it's argued for by noticing that this is the unique element of the Q cohomology with 3 factors of lambda. And the terms that should contribute in the amplitude in the end, they should lie in the Q cohomology. Yeah, I mean, it should be Q closed because the expression we started with is a product of Q closed vortex operators. And it should also be the case that Q exact pieces shouldn't contribute because this ensures gauge invariance. So this is then the only term that contributes, and the zero mode prescription effectively boils down to projecting out the coefficient of the of order lambda cubed and theta to the 5 out of this term, which we are left with after the weak contractions. And then, of course, you need to integrate over the positions of the integrated vortex operators. Okay, so this is kind of the review of the procedure how to calculate correlators or tree-level correlators in the minimal pure spinor formalism. Now let me tell you first kind of how to adapt this to purely closed string disk amplitude. So a disk amplitude where we only scatter closed strings. This is what we did together with Andreas Bischoff. I should say there were also some earlier results on the disk, but these were 3-point function of 1 closed and 2 open strings. And this avoids kind of a small subtlety that I come to in a moment when you kind of want to fix the conformal killing group. So concretely, we look again at type 2b with the p branes, which are spanned along the first p spatial dimensions. And a reminder, the vortex operators of the closed strings are have this product structure of the vortex operators of the open string. But now on the disk, this variable z here lives in the upper half plane. And we deal with this right moving part of the vortex operator in a similar way as you are used to from the INS theory by employing the doubling trick. So we extend the X field to the full complex plane, including also the lower half plane where Z bar lives in. We extend it basically by the value of X bar, the right moving part of X at the same plane at Z bar. But in order to obtain the correct boundary condition between the left and right movers, we have to distinguish between those directions where you have Neumann boundary conditions and Dirichlet boundary conditions. And this introduces this D matrix here, which also featured yesterday in Priscilla Marcus' talk. Okay, so this is, as I said, should be well known for everybody who ever did a disk amplitude in the RNS formalism. And this doubling trick can be extended to fermions. This is also reminiscent of the calculations in the RNS formalism, where the relevant fermions are the spin fields. But we generalize this now to the spinors that we have in the pure spinor formalism. The psi here stands for an arbitrary spinor with either this upper index or lower index, and as I said, these differ in their chirality. We don't really need to know the explicit form of these analogs, fermionic analog or spinorial analogs of the D matrix here. It's sufficient to know some relations between the D matrix M and N, which can be derived by asking for consistency of the OPEs. And these relations allow to rewrite the right moving parts of the closed string vortex operators here in terms, so which to start with are expressed in terms of X bar and theta bar and everything bar, lambda bar. You can use the doubling trick to write everything in terms of the unbarred fields X, theta, which were extended now to the full complex plane. And the only effect which is in the end effectively remaining is that the polarization vectors, the momenta, are multiplied by this D matrix. And then of course you still evaluate it at the position, at your original position Z bar. Same holds for the integrated vortex operator. So the advantage of doing this is then you can use the same contractions as I showed you before. It's just that now the fields can also depend on Z bar. And here's now the little subtlety I mentioned earlier concerning the conformal killing group, PSL2R. If you want to fix this, then this allows to fix only 1.5 closed string. Yeah, if you have one closed and two open, you can fix the closed one and one open. Then the full conformal killing group is fixed. But here you cannot do that. So what we propose is that indeed you fix one of the closed string vortex operators. So you use an unintegrated one, but for one second one, you have to use this mixed representation of the vortex operator, where one form is like for the unintegrated one, and the other one is like for the integrated one, the more complicated one. Even though you should notice that both now depend on a variable, a real variable that we are still integrating over.
Sorry.
Yeah, bitte. Sorry?
5 minutes.
Yeah, okay,
more.
Sure. And well, tau p, I should say, is a tension of the p brane. Oh. Yeah. So this is also reminiscent of the RNS, how it works in the RNS theory, and we followed some analysis by Hugoven and Skandaris in arguing for this formula. Maybe I don't, if you have time, go into any more details here. This can now then be applied. I mean, we applied it until now only to the very low point function, the 2-point function, and the 1-point function. So for the 2-point function, again, here are our two closed string vortex operators. One is fixed to z equals I, the other one to I times y, which still has to be integrated over. Then you use the forms of the vortex operators for the unintegrated and the integrated one. You have to perform all the Wick contractions, and this leads you to the following expression. This is a usual Kober-Nielsen factor that you also know from the RNS calculation. Also, these denominators here arise from the Wick contractions. And after the Wick contraction, you are still left with a zero mode integration. And this is kind of hidden in these numerators, D1 to D3 here. These are kinematic factors that give you the kinematic factors of the result. I'll just give you an example for D1. It's some product or sum of two terms, which each of them are products of these superfields, which appear in the vortex operators. So this is an A alpha because it's contracted with lambda alpha. This is an AM because it's contracted with a momentum. And again, you have to expand all these superfields now in theta. You get all kinds of different powers in theta. All these terms have 3 lambdas from the 3 fixed vortex operators, or unintegrated vortex operators. And then you have to use a zero mode prescription to pick out the terms which are of order theta to the 5th. And this is kind of where the bulk of the calculation is. And this is complicated. For this, one typically uses the help of a computer, and we use the very useful program by Kaspar Peters called Cadabra, which is really very well suited for this kind of calculations. This is a result. The details are not so important. These are gamma functions. Q, little q is this combination of momenta. D is a D matrix I introduced before. T is again some scalar product of momenta. The exact form of A1 and A2, which depends on polarizations and momenta. So these are kinematic factors which arise from the zero mode prescription here. The concrete form is not so important. What is important is that this gives the same result as what people found in the RNS format calculation in the 90s. Now, very shortly, 2 slides about the 1-point function. So there was earlier work on the bosonic theory and in the RNS theory from the 80s. Now we also wanted to do it in a pure spinor formalism. And there's one obvious obstacle here, it seems. Namely, if you just have one vortex operator, one closed string vortex operator, even if you take it in this form that the vortex operator is unintegrated, you only get 2 factors of lambda. Yeah? But the zero mode prescription needed 3. And the way out here is that there is actually an alternative zero mode prescription, which was discussed by Berkowitz 5 years ago. It's equivalent for higher point 3 amplitudes. It works for 3 amplitudes. And it's equivalent for higher point functions, but it seems it's not equivalent for this 1 point function, because the old prescription, which needed 3 lambdas, would just give 0, whereas this one has a chance to give non-zero. So this alternative zero mode prescription tells you to take out of this term that you obtain after the Wick contractions, not any term which contains any lambdas and thetas, but just the constant piece.
Sorry, and interrupt you. There is no time left for your talk. So
okay, I wrap up. I wrap up. Sorry for that. I need 2 more minutes. Yeah, this is the only alternative scalar element in the Q cohomology. So this is an alternative zero mode prescription, which again, you don't want to have any lambdas and thetas in your expression in the integral. So you have to use the integrated form of the vortex operator. So you still integrate it. You have to divide by the volume of the conformal killing group, which is infinite. And you can deal with this problem like in the RNS formalism. You fix the position of the vortex operator and only divide by the volume of the subgroup of the conformal killing group, which leaves the position invariant. And this subgroup has finite volume. If you do this, you end up with this result. And again, it's the same as in the RNS formalism. And so you see that this alternative zero mode prescription is important for doing this 1 point function. There was an alternative proposal at the same time as our paper, how to deal with this problem. But unfortunately, I don't have time to discuss this. So let me just come to the outlook. I discussed with you disk level amplitudes of fields which correspond to NSNS fields in the RNS formalism. Of course, I also told you that the pure spinor formalism is particularly powerful if you want to deal with Raman-Raman fields and fermions. So this would be an obvious next step. Also, we would like to generalize these methods to the projective plane and also to higher endpoints. As I told you, my main motivation was higher derivative corrections in DBI, and these might require higher endpoints, as we discussed earlier. Okay, so sorry for running over time, and thank you very much for your attention.
Thank you very much. So we have just 2 minutes, maybe one question. Mm-hmm. Please, there is a question. So there's no question. Thank you very much.
Okay. Yeah. Thank you.
So we go to the next talk, which is Chris Hall, and he will talk about gravity above the Planck scale. So you start at 18:30, and you have 40 minutes and 5 minutes for the discussion.
Okay, thanks very much. So I'm very pleased to be back at a real physics meeting again, and I would like to take this opportunity to thank the organizers for all the hard work they put into putting this meeting together under such difficult circumstances. And I think it's really paid off, and I think it's been really great to be back at perhaps one of the first major European meetings after the lockdown. So I'm going to be talking about some speculative ideas about gravity above the Planck scale. So I want to raise the question about what happens at the Planck scale and beyond. And in particular, could there be, although we understand gravity rather well at low energies and large distances, there's a possibility that there could be a radically different theory beyond the Planck scale at energies above the Planck mass or distances below the short smaller than the Planck length. And one idea which has been thought about is that there could be some highly symmetric phase, which is some transition to a highly symmetric phase. In the context of string theory, there's been the idea that maybe there's some kind of tensionless string where the infinite tower of massive modes of a string, or some of them, will become massless, and you end up with a theory with infinite number of gauge fields, infinite number of symmetries. And some time ago, Gross and Mende looked at high energy scattering of strings and found evidence that there could be some sort of structure of this kind. And more recently, there's been a lot of progress in this direction, and there's been particular models where it's now understood that there really is some such tensionless string transition. And so this is a distinct possibility, and recent work has been very interesting in that. But I'm not going to say more about that today. But another idea which has been thought about by many people over the years is that the fundamental theory should be, at the most fundamental level, be conformal. And it should be something which doesn't have any fundamental length scales. And in both these cases, the idea would be that there's this large symmetric structure beyond the Planck scale would be spontaneously broken to make contact with the physics which is familiar. So in particular, conformal invariance, or more properly local scale invariance, the idea that, as I mentioned, the idea that it could be a fundamental theory, a fundamental symmetry of the theory appears very, very attractive. In this picture, the Planck scale, and in fact all other scales, would emerge from various symmetry breaking mechanisms, and so there would be some spontaneous symmetry breaking, so there would be consequences of the background rather than fundamental. One of the immediate problems with this, that if you're looking in the context of gravity as a theory of a metric, the conformal gravity in 4 dimensions and higher is necessarily a higher derivative theory, and that has a lot of problems associated with it. In particular, it has ghosts, and moreover, there's problems with understanding how such a higher derivative theory would lead from that familiar Einstein theory could emerge at low energies. Although there's been lots of interesting ideas in that direction. But another possibility is that maybe gravity at the most fundamental level is not a theory of the graviton at all. It's not a theory of a massless spin 2 particle. We know at low energies, there's very good evidence that it's described by a spin 2, massless spin 2 particle, although there's some interesting ideas about the possibility of it having a very small mass in 4 dimensions. But one idea is that maybe this gravity is not fundamental, that may be emergent from some more fundamental theory, or even more radically, that space-time itself might be emergent. There might be some sort of discrete structure from which space-time emerges. And both of these ideas are things which have been or will be addressed by other speakers in this meeting. I'm going to be talking about perhaps a more modest possibility, which is that perhaps gravity could have an ultraviolet origin that is a theory of a different field in moving in a space-time, perhaps in more than 4 dimensions. And this would have to be something which would give rise to the familiar theory of gravity in 4 dimensions. But if such a thing were possible, then maybe this could allow conformal invariance, and this idea, I think, is one I want to try and address. So, an analogous theory would be whether Yang-Mills theory is really a theory of gluons, a theory of non-abelian vector fields. We know that four-dimensional Maxwell theory can arise from a p-form gauge field in higher than 4 dimensions by compactification. And interestingly, we know that four-dimensional Yang-Mills, so that four-dimensional Yang-Mills with its complicated interactions can arise from a six-dimensional non-Lagrangian theory, which is not a theory of a vector field, and in fact is in some sense related to some non-abelian generalization of a two-form gauge theory. So more precisely, there's a precise realization of this, which we now have very good evidence for in the context of supersymmetric theories. If we think about four-dimensional maximally supersymmetric Yang-Mills with n equals 4 supersymmetries, this arises from a six-dimensional theory with 2, 0 supersymmetry. In 6 dimensions, the spinors can be chiral, and P, Q supersymmetry means a superalgebra where you've got P right-handed supercharges and Q left-handed ones. So this means it's got two left-handed supercharges, each with 8 components, so we get 16 components of 16 supersymmetries. So there's a free theory with this in 6 dimensions, which has got 2, 0 supersymmetry, which includes a two-form gauge field whose three-form field strength H, given by the curl of B, is given by, or the exterior derivative of B, is, in the linearized theory, is self-dual. So the three-form is equal to its Hodge dual. And this theory reduces to four-dimensional n equals 4 supersymmetric Maxwell theory, and in particular, the two-form reduces to a one-form. So rather remarkably, we have very good evidence that there's an interacting version of this, which gives rise to, which reduces to four-dimensional super Yang-Mills, and the interacting theory is a super conformal field theory in 6 dimensions, and is non-Lagrangian, which means that it's a phrase which means that it's not a conventional field theory with a local covariant formulation. It's something more exotic, and we don't yet have a direct construction of that. But from string theory, we have very good arguments that this theory exists as a well-defined quantum field theory, a superconformal field theory. And in 6 dimensions, it has interactions which are associated with a gauge group, which can be of the ADE family. And these gauge groups then give rise to the Yang-Mills gauge group in 4 dimensions. And it's very remarkable that this theory has conformal invariance in 6 dimensions. And when you compactify on a 2 torus down to 4 dimensions, there are symmetries. There's an SL2Z symmetry on that coming from the large diffeomorphisms acting on the 2 torus. And these diffeomorphisms on the 2 torus give rise to precisely the S duality, SL2Z S duality of 4-dimensional super Yang-Mills. And one of the ways of understanding how this theory arises is that it arises as a strong coupling limit of 5-dimensional super Yang-Mills. And so it can be understood within the context of the 5-dimensional theory that rather remarkably at strong coupling with, strong values of the Yang-Mills coupling, an extra dimension emerges, a bit like in 2A string theory, an extra dimension emerges, and giving rise to this 6-dimensional superconformal field theory. So I'll say more about this in a moment. But the idea I want to follow is that there could be a similar story for gravity. And rather remarkably, there's a structure which works in complete detail, in complete analogy with what we've just seen at the level of the free theory. And so then there's a question about whether this has an interacting analog. So it turns out that at the free level, there's a superconformal field theory in 6 dimensions, which has got 4, 0 supersymmetry, and hence 32 supersymmetries, 32 normal supersymmetries, and because it's conformal, it also has a further 32 conformal supersymmetries. And the highest spin field in this is a gauge field which has 4 indices, and I'll say more about that in a moment. But the symmetry structure is the same as that of the Riemann tensor. So 2 pairs of antisymmetric indices, and it's symmetric under interchanges of the pairs. And remarkably, this theory in 6 dimensions, although it doesn't include a graviton, dimensionally reduces to 5-dimensional linearized n equals 8 supergravity. So it's it's in complete. So it works in exactly the same way as the relationship between the free 2-0 theory and the 4-dimensional Maxwell theory. So this raises the question about whether there could be an interacting analog. We don't know directly how to write down this non-Lagrangian theory. In this case, we just have indirect existence arguments for its existence. In this case, again, we can't write it down explicitly. We can show that it can't be a conventional local covariant field theory. There's no way of writing such a theory down. But whatever the method by which the 2-0 theory could exist, maybe that could lead to interactions for the 4-0 theory. Just as we saw for just as for the 2-0 theory, it arises a strong coupling limit of 5-dimensional super Yang-Mills. I want to argue that this could arise as a strong coupling limit of 5-dimensional supergravity. And so here's the possible, and because it's a superconformal field theory, there's a possibility that this could be a conformal theory of gravity. It's an exotic conformal theory in 6 dimensions, which nonetheless makes contact with 4-dimensional Einstein theory on compactification. And so this would be a theory which at the fundamental level would have the conformal invariance I was asking for. And if this could be achieved within the context of M theory, so for example, compactifying M theory on a torus down to 5 dimensions, so we get an ultraviolet completion of the 5-dimensional supergravity, and then looking at the strong coupling limit of this, in which you take a limit in which the 5-dimensional Planck length, the Planck scale becomes strongly coupled, could give rise to a highly symmetric 4,0 phase of M theory. So the contents of this talk are mostly based on a series of papers I wrote some time ago, the 3 most relevant ones being these 3, and some other papers I wrote about the same time. But what I want to do is take this opportunity to revisit some of these ideas based on what we know now, and try and see whether there's some further way of trying to understand whether there could be evidence for this rather remarkable structure, or ways of telling whether or not such a structure really emerges in M theory. So one way of thinking about this story is as follows. As many of you will be familiar with, there's a way of thinking about gravity as Yang-Mills squared, that roughly speaking, you can understand the construction of gravity from 2 copies of Yang-Mills, or and extending that to supergravity coming from super Yang-Mills. And if you think about it in a Young tableau, Yang-Mills is given by a vector potential represented by a Young tableau with a single box. Taking the product of these 2, you get you can get a symmetric product of these. You get a Young tableau with 2 boxes representing a symmetric tensor. And this, of course, emerged originally from string theory, where there's a picture of the closed string as, at least at the level of the Fock spaces, as the tensor product of 2 open string Hilbert spaces. And in the same way, if you think about the 2-0 theory, it's a theory of a 2 form, so it's given by a Young tableau with a column with 2 boxes. And if you were to take the 2-0 theory squared, you get the product of this with the product of this, giving rise to an object with 4 indices and the symmetry structure indicated by this Young tableau. As we'll see, as I'll review in a minute, reducing the 2-0 theory, the 2 form reduces to the 5-dimensional theory of a photon plus a dual photon, and this gives rise to a 5-dimensional theory of a graviton, and together with duals of the graviton, which I'll say more about in a moment. And another part of the story is that there's can be thought about from the 5-dimensional superalgebra. It could be written in this way. So here, alpha and beta are spinor indices. C is the charge conjugation matrix, and omega is the antisymmetric invariant under the SP under the symplectic R symmetry group. And so this has some interesting central charges, and the reason why they're interesting is that BPS states will carry one or more of these central charges. For Maxwell fields in 11 dimensions, in 5 dimensions, they carry electric charges, and these Zs could be associated with the electric fields for the Maxwell fields, the electric charges for the Maxwell fields. And if this 5-dimensional theory arises from a 6-dimensional theory, the kind of a 2-0 or a 4-0 theory, then this charge K will be could be shown to be the one associated with the momentum in the compact 6th dimension of the Kaluza-Klein modes. But from the point of view, so if it's going to have a 6-dimensional origin, you need to have BPS states carrying this. If it's going to have a p, 0 6-dimensional origin, a theory would have to, the theory in 5 dimensions would have to have BPS states carrying this charge. In the super Yang-Mills theory, this is carried by some BPS solitons, which arise from Yang-Mills instantons. So if we think about Yang-Mills in 4+1 dimensions, and we take a spatial slice, you get 4-dimensional Euclidean space. And if you consider a Yang-Mills instanton in that space, in that Euclidean space, it's localized in 4 dimensions. And if you take the product of that with time, it looks like a naught brane in 4+1 dimensions. And turns out to be a BPS soliton, sometimes called an instantonic soliton, or sometimes just an instanton, which is a bit of a misnomer. But these are BPS states carrying this charge, and in the strong coupling limit of super Yang-Mills, these BPS solitons arising from these instantons become very light, and in the limit they become massless, signaling the decompactification of the extra dimension, so that these are associated, these BPS solitons are associated with the Kaluza-Klein modes. And you could ask, and so the question arises in the context of whether or not the 5-dimensional theory has got such a strong coupling limit. There's a question about whether such BPS states carrying this charge K arise in the 5-dimensional supergravity, or in the context of M theory compactified on T6 down to 5 dimensions. And so and then there's a question that then arises whether they become massless at strong coupling. So if we look a little bit in a little bit more detail at some of the things I've introduced, the Maxwell field in d dimensions is given by a photon. It's the dual photon, which is an n form where n is the dimension -3, whose field strength is the dual of the field strength of A. So it's totally antisymmetric, so it's given by a Young tableau with n boxes. The magnetic charges are carried by d-4 branes, which couple to this potential, and this gauge field A in general can have Dirac strings, or if there are magnetic charges carrying this, then this A will have Dirac strings, or more properly can be thought of as a connection on a non-trivial bundle, and the A tilde will be well defined. If there are electric charges, these are carried by electrically charged naught branes, charged particles coupling to A, then the potential A is then well defined, but A tilde would in general have direct string singularities. This picture works well in the free theory. For the interacting theory, there's no non-abelian theory for the dual photon, but we know nonetheless that such a phenomenon must exist. That, for example, in four-dimensional Yang-Mills, there's a dual photon which will be again another one form, which a dual gluon, which arises, for example, from S duality. If you go from weak coupling to strong coupling, you go from a theory at weak coupling, which is a theory of A, to a theory at strong coupling, which is a theory of A tilde. There's a similar story for linearized gravity, where you have a graviton given with this Young tableau, whose field strength is the curvature tensor, and there's a dual graviton which has you dualize one column to replacing it by one with n indices, or you dualize both columns, the double dual graviton. And there are corresponding curvatures where you get add one more index to both columns and then to symmetrize appropriately. And these field strengths will then so the duality is defined by having these field strengths dual to each other. The single duality is given by a dual of the curvature tensor, and the double one by a double dual. So this means you're dualizing the first two indices and the second two indices. So this was dualizing both of them. And this duality exchanges field equations of Bianchi identities in a rather nice way. And the usual picture would be where you'd have electric style sources for H, in other words, coupling to the stress tensor, and none for the dual graviton, which might be T tilde. If you included magnetic sources, there would be direct strings for H, and if you included electric sources, there would be direct strings for H tilde. So the whole picture in the free theory is very similar to that in the Maxwell theory, and in fact, these ideas for looking at the these ideas for the structure of the dual versions of gravity, in fact, emerged from this the work I was looking at in on the 4-0 theory. So it's one of its successes was leading to the idea of dual gravitons. So if we look at the free 2-0 theory, it has an R-symmetry which is SP2 or USP4, and it's superconformal, so it's invariant under this superconformal group. It has the self-dual 2 form, 5 scalars and 4 fermions. And when you reduce to 5 dimensions, the 2 form gives rise to a 2 form and a vector field. But the self-duality in 6 dimensions means that the field strength of B is the dual of the field strength of A. So this means that these two are not independent, so you can regard it as just the theory of the vector potential, for example. And then we get precisely the spectrum of the vector multiplet. And reducing to 4 dimensions, you get that you get 2 photons which are related, whose field strengths are dual to each other, and that means it's essentially one vector field, and but they're acted on as a doublet of SL2Z, and so one is a dual of the other, and so we see that the SL2Z is realized as an electromagnetic duality. The SL2Z of diffeomorphisms of the 2 torus are realized in that way. For the 4-0 multiplet, there's a similar story. The little group in 5+1 dimensions is SO4, or SU2 cross SU2, and the states will then be in representations of this and the R-symmetry group USP8, and it fits into these representations. And note that everything is a singlet under the second SU2, And these correspond to a set of light cone fields where you've got, these are SU2 indices, and these are symmetric tensors in these SU2 indices, and antisymmetric in the ABCD indices. And the covariant versions of these are given by tensors like this. So this, here we see that we've got the 4-index gauge field and a higher spin generalization of a gravitino. So the 4-0 theory at the free level has a spectrum of 42 scalars, 27 self-dual 2 forms, and a gauge field whose field strength is given by taking 2 derivatives and antisymmetrizing on one of the derivatives with the first 2 indices and one of the derivatives on the second 2 indices. And this is this field strength is required to be self-dual on the first 3 indices and self-dual on the second 3 indices. And this gives a supergravity theory, a supergravity type theory, but without a graviton, but instead with this field, and a very large superconformal symmetry group. But nonetheless, it reduces down to gravity. If we take the 4-index tensor and reduce on 5 dimensions, you get 3 fields, one with 2 indices, one with 3, and one with 4. But the self-duality implies that these are, this is the graviton, this is the dual graviton, and this is the double dual graviton. So only one of these is independent, and so it can be regarded as a theory, say, of just H mu nu. In other words, we get precisely the spectrum of the 5-dimensional n equals 8 supergravity. So we get the vectors from the BMN, the graviton from this, and an important thing is that the B fields don't give rise to any scalars, and this field doesn't give rise to any scalars. And the diffeomorphisms in 5 dimensions arise from the gauge transformation of this C field, which, because it's got more indices, the parameters have got more indices, and it has the parameters have got 3 indices with this Young tableau. And again, if we reduce down to 4 dimensions, there's a similar story where we get the vector fields in doublets of SL2Z, and we get 3 gravitons, the graviton, the dual graviton, and the double dual graviton, which are related which form a triplet under the SL2Z coming from reducing on the torus. So we get an interesting version of S-duality in this theory, which at least at the free level. So now I want to say something a bit more about the arguments that these can arise at strong coupling. First of all, for the Yang-Mills theory, if we look at the Yang-Mills theory in 5 dimensions, here's the superalgebra again. The electric charges are carried by, for example, W bosons of the Yang-Mills theory if it's spontaneously broken, and the K is carried by these Yang-Mills instantons lifted to become BPS solitons in 5 dimensions. And this charge K is proportional to the instanton number, and these fit into a short multiplet. And their mass is given by, up to a constant of proportionality, is given by the instanton number divided by the Yang-Mills coupling squared. So in 5 dimensions, Yang-Mills coupling is dimensionful, and so this is Yang-Mills squared has got the dimensions of a length. The Yang-Mills coupling squared has got the dimensions of a length. And here we see that at strong coupling, if as the Yang-Mills coupling constant goes to infinity, this becomes light. But this becomes these become light, and these could be identified with a spectrum of a Kaluza-Klein tower for a 6th dimension. And so what's been argued is that this is indeed what happens. There's really a 6-dimensional theory where, as the Yang-Mills coupling constant goes to infinity, the radius of this extra dimension goes to infinity and it decompactifies, and these instantonic solitons are interpreted as the Kaluza-Klein modes. The 5-dimensional theory is non-renormalizable, so it doesn't exist as a quantum theory on its own, so it needs to be embedded in another theory, it needs to be embedded in it needs to be provided with an ultraviolet completion, and it can in fact be defined within string theory. For example, it arises as the world volume theory of a D4 brane, at strong coupling limit is defined within string theory. The D4 brane lives inside the 2A string theory. At strong coupling, the 2A string theory becomes 11-dimensional M theory, and the D4 branes lift to M5 branes wrapped on this extra 11th dimension. And so the world volume theory of these M5 branes is six dimensional and indeed has the 2,0 supersymmetry. So we see that the D4 branes lift to M5 branes, and we see that within string theory this is precisely what happens at strong coupling, because the Yang-Mills coupling of the Yang-Mills theory on the D4 branes can be related to the string coupling constant of the 2A string. As I mentioned, there's no direct construction of the interacting 2-0 theory, but this picture within string theory shows that this must be what happens. This, together with other arguments, shows us this must be what happens. And more precisely, when we're talking about a coupling constant becoming large, when it's dimensionful, it's not quite what one means. What one really means is one's looking at energies which are large compared to the Yang-Mills scale. Or in other words, we're looking at taking the energy scale times Yang-Mills coupling squared to infinity. So what this means is really what we're looking at when we say we're taking the strong coupling limit. What we're looking at is the physics at energy scales larger than the Yang-Mills scale. So what happens in the supergravity theory at strong coupling? So the supergravity theory, again, is not a well-defined, again, needs an ultraviolet completion. So we imagine it embedded in string theory or M theory. And if there are BPS states carrying this charge K, their spectrum will be of this form, and integers divided by the 5-dimensional Planck length. And so these would become light in strong coupling, which would be which is really, again, is really a high energy limit where we're looking at energies large compared to the 5-dimensional Planck scale. And so if there are states so a necessary condition should be that there are states carrying this charge K. And and if they have the right spectrum to fit into a Kaluza-Klein tower, then the theory should there's strong evidence that the theory should decompactify to a 4,0 theory in 6 dimensions. So if you consider boundary conditions where the 5-dimensional theory is compactified on a circle, there are indeed states carrying K, which are the Kaluza-Klein monopoles, and the Zs are carried by the naught branes. And the full 5-dimensional M theory the full theory of M theory compactified down to 5 dimensions, then on a further circle, then has a U-duality symmetry, which includes a duality which relates the 5-dimensional momentum to this charge K. So this charge K is certainly part of the story when we in that context. And for higher than 5, in 5 dimensions and higher, then this charge is given by a D-5 form, and again this is carried by Kaluza-Klein monopoles. And there are explicit forms for this charge, but maybe I'm running short of time, so I won't talk about that today. So M theory compactified on T6 has the 5-dimensional supergravity as its low energy limit, and the naught branes and 1 branes in 5 dimensions lift to self-dual strings in 6 dimensions. And the tension of these would go to 0 in the strong coupling limit. So this suggests that this strong coupling limit would also be some kind of tensionless string theory. or associated with some sort of tensionless strings. And so in this way, there's a possibility that the strong coupling limit of this theory could give a highly symmetric phase of M theory with an exotic conformal gravity and 4,0 superconformal symmetry. So the key thing is, the key question is whether M theory compactified on T6 has BPS states carrying this charge K. And this is, if there are no such states, then what I'm suggesting can't happen within M theory. So it's a very interesting question, which is about the BPS spectrum in M theory, about whether there are really states in 5 dimensions, in 5-dimensional Minkowski space, which carry this charge K. For example, they might be arising from something like zero-size gravitational instantons in 4 Euclidean dimensions, a product of those with time. And so one of the things I want to emphasize in this talk is that there are questions which could be asked about the BPS spectrum of M theory, which could rule out or provide some support for the conjecture which I've been, the possibility of there being such a phase that I've just described. How much time do I have left? Okay, so I'll skip what I was going to say about the symmetries of the theory. I've been talking about the possibility that there could be the possibility of there being 4-0 6-dimensional superconformal field theories in the same way as there are ones with 2,0 supersymmetry. In both cases, there's no local covariant interacting field theory, so these are necessarily non-Lagrangian and so rather mysterious. But there's in both cases, the mechanisms would work in a very similar way. BPS electric naught branes and magnetic strings would lift to self-dual strings in 6 dimensions, which become tensionless whose tensions goes to 0 in the conformal limit. And that's an important part of the 2-0 theory already. And there's a large superconformal symmetry. The 4-0 theory has 32 plus 32 supersymmetries, 32 normal ones and 32 conformal ones, which, giving 64 in total, which is I think it's the only case where there's a possibility of a realization of that many supersymmetries. 64 supersymmetries. And it's rather interesting that in both cases, the key gauge fields in 5 dimensions lift to self-dual tensor gauge fields with exotic representations. And in both cases, the 5-dimensional Yang-Mills scale and the Planck length both emerge from the 6-dimensional radius. And the 6-dimensional theory has got no intrinsic scale, and all the scales arise from compactification. So at the level of what we can say about the 5-dimensional theories and lower, the story of dual gravitons and gravitational S-duality work well for the free theory. In particular, the charge K is carried by Klutzer-Klein monopoles and branes which arise from D equals 4 instantons, Yang-Mills instantons or gravitational instantons, and is related in a way which I haven't had time to explain, but is talked about in the papers, to the nut charge, and this is properly interpreted as giving the magnetic charge of the Klutzer-Klein monopoles. For the 4-dimensional super Yang-Mills or linearized supergravity, there's an S-duality which arises from the 2-0 or the 4-0 theory compactified on a 2 torus. And so there's a very elegant story which works very well at the level of the free theory. So the question then arises as whether or not there really is something which arises, whether there is an interacting version of this, whether there really is a full zero theory or whether or not. So a key issue is the spectrum of BPS states which carry this charge K. If the M theory compactified on a torus has no such states, then there would not be any strong coupling phase which would have the full zero supersymmetry, because there would not be the states which would provide the Klutz-Klein modes. On the other hand, if there were states carrying this state discharge K, then that would be strong. That would be very good evidence that this idea is moving in the right direction, and that there could be an extra dimension arising in strong coupling. And if this really does arise as a limit of M theory, then this would be a theory with vast symmetry and many unusual features. And maybe it may mean that the right way to think about M theory is not as a 11-dimensional theory, but maybe as a 6-dimensional theory in this highly symmetric phase. And that as you break some of the symmetries, then you see and take various limits, and then extra dimensions can emerge in a way which has become well understood within the context of M theory. And rather intriguingly, it suggests that the arena is not the usual space-time, or at least it doesn't carry the usual structures. It doesn't have a metric, but instead the metric is replaced by this exotic tensor, and the diffeomorphisms are replaced by instead of symmetries carried by vector whose parameters are vector fields, they're replaced by gauge symmetries which have parameters with 3 indices. And it's very interesting that there's that even the possibility of a theory of gravity which has conformal invariance and an exotic description in terms of very unfamiliar structures, and yet which has the potential to give rise to familiar structures of Einstein gravity when you compactify down to 4 dimensions and look at it at low energies. So thank you for your attention.
Thank you very much for a nice talk. And we have some time for the questions. So in the auditory, yes, go ahead.
Hello, Chris. Thanks for the very nice talk. I would like to ask, is there in this gravitational S-duality that you discuss, is there a theta term? Because I think in one of your papers there is some theta term that you discuss.
Yes, so I mean I haven't had time to go into the technicalities, but yes, there is. I mean, a theta term is natural in this context, and one can understand what happens at the level of the free theory, but the story is very similar to Super Yang-Mills, where the Maxwell theory has an SL2Z symmetry of the equations of motion, but the interacting theory doesn't, and you need to work with, and it's really only at the quantum theory where you find that nonetheless there's a mysterious and rather non-local SL2Z symmetry, which indeed is a key to understanding the strong coupling dynamics of that. And so the hope is that, well, the possibility is that there's a similar structure could arise in gravity, in which there's the duality between the in which going to strong coupling would lead to a theory in which the dual graviton is playing a role similar to the way the dual photon would be playing a role, or the dual gluon would be playing a role. And it's difficult to be precise until we can write down a lot very explicitly at the level of the free theory, but it's I think it's be a very interesting understanding some of what happens, what could be understood at the level, even at the level of the interacting theory in 4 or 5 dimensions. And there's been a lot of interesting work by you and others looking at such theta terms, and I think that's a very interesting way to try and explore further.
Thank you. More questions? Okay. Yaron.
well, you made several interesting remarks. I was wondering if along these lines you could contribute in the discussion of finiteness of n=8 supergravity. You at some point,
So I don't think this story has anything new to add to that. I mean, in my mind, so if n=8 supergravity turned out to be finite in its own right, then there'd be a whole other story. I'm just working with the assumption that the ultraviolet completion is given from string theory. If there's a subsector of that at which decouples and gives its own finite theory, then that would be very interesting. But I think that this doesn't have any light on that. But it'd be very interesting. One thing which is very interesting is if this false zero theory does exist, because it's conformal. There's a possibility. There's a question then about whether it's super conformal at the quantum level, and there's a possibility that the six-dimensional theory being conformal could really be a finite theory, and that would be very exciting. For the four-dimensional theory, n=8, it requires an infinite number of miracles, and we've already seen that there's a lot of miracles have already happened, and a lot of divergences are absent, but it's expected that there's an infinite number of possible divergences, each of which has the coefficient would have to be 0, and at the moment we don't have any argument that they should be 0. So I think we see something else. The expectation would be that the n=8 theory, there's no reason to believe that, to my mind, that it should be finite, but it would be very exciting if it was.
Thank you. So there's one more question there.
Thanks, Chris, for the lovely talk. So you explained how in the free 4,0 theory, it's naturally given in terms of a dual graviton, a mixed symmetry tensor field, right? So I'm wondering, because it's free, you would expect you can just dualize it. So have you considered this, and do you get anything interesting if you dualize it so that it looks like an ordinary graviton?
So yeah, so in 5 dimensions, so the story is, so let me just go back to the slide. So in 6 dimensions, the field strength is self-dual on both these columns. So if you dualized it, you just get back to where you were. So it's like if you look at the 3-form gauge field in 6 dimensions, because it's self-dual, dualizing it doesn't give anything new. When you looked at, when you reduce down to 5 dimensions, the 2-form field, if it wasn't self-dual, would give rise to 2 fields, a 2-form and a vector field. But then this, the self-duality means that the 2-form here is the dual of this vector field here. The field strength of A, F, is the Hodge dual of the 3-form, which is the field strength of B. So you get the 5-dimensional duality arising from this. So the theory you get in 5 dimensions is essentially a democratic formulation where you get both the B field and its dual, and they're both there, but there's a constraint, meaning that there's only one independent degree of freedom. And the similar thing is happening here. Reducing the 4-index object, you get 3 fields in 5 dimensions, and the graviton, and then the self-duality conditions in 6 dimensions means that this field is the dual graviton for this field, and this is the double dual graviton. So you're getting gravity in a sort of democratic formulation where you get the graviton and all its duals, but then there's the constraints which imply that there's only one of them which is independent. So the answer is in 6 dimensions, everything's already dualized because it's self-dual. But in 5 dimensions, the duality is central here and plays a key role. And also there's a similar story when you reduce down to 4 dimensions, which is also very interesting.
Thanks, that clears it up for me.
Thank you. So to be democratic, maybe we will ask if there is questions in on the website on the internet. No question. So thank you very much, Chris. Thank you. Very interesting. So we will shift to the last talk of the evening section, and it is Yaron, who will talk about entanglement, chaos, and quantum computation. Hello, you listen us?
I can hear you, but can you see me? Because
Yes,
I'm unable
to hear you, but not yet see your screen.
The host has stopped my video. Can you open it? I get a message that I'm unable to start the video. The host has stopped it.
Now
Okay.
we see you.
Okay. Thanks. So let me share the screen first, and can you see the screen? 1 second.
Not yet, just a moment. We need some time. So the file is here.
I cannot see you for some reason. Okay. Can you see the screen?
You should share your screen.
Yeah. I try to share it. Let me do it again.
Okay, now we see your screen.
Now you see? Okay.
Let's make it a full screen. Yes. Okay.
Now?
We see.
Okay.
So
thanks a lot. Okay.
you have 40 minutes and 5 minutes for discussion. So please follow the time schedule. Thank you.
Okay. Thanks a lot for the invitation. Actually, it's a pity that I'm in the East Coast and I cannot join you in Corfu. But next time. So I want to talk about quantum computers, and it's something that I've been looking at in recent months together with Juno Kim from Princeton and Ari Rosa from South Korea. These are these 2 papers and some to appear. And quantum computers have attracted actually a lot of attention recently, definitely in the news, because there are many companies trying to build them, but also in our community as models of quantum black holes and also in condensed matter. So there is a whole interesting story going on there. And I would like to share with you some of the excitement. I will be very basic and maybe a little bit more technical towards the end. And the outline of the talk is going to be what are actually quantum computers? What are the basics of this? And then I will discuss the issues of entanglement and chaos. How do they affect and how they're implemented in the models of quantum computation and some of the challenges. So let me begin with the basic. Classical mechanics. Classical mechanics is the field theory that describes large objects, and it's a deterministic theory. And actually, the classical computer is based on this classical mechanics paradigm. So the classical computer uses bits to represent its values. A bit can be either in a state 0 off or a state 1 on. And at any point in time, the state of the classical computer is just described by numbers of zeros and ones. Quantum mechanics, as we know, is definitely quantum field theory. And it is also not deterministic, it's statistical, and it is the paradigm behind quantum computing. In fact, it was already in 1982 that Richard Feynman suggested it as a tool to study the dynamics of quantum system, because he realized that classical computers will be too limited to study the huge number of degrees of freedom that you have in a quantum system. And indeed, quantum computer uses an object which is called a quantum bit or a qubit. And a qubit can take not just the values 0 or 1, it can take any linear combination of them, as we are used to in the usual superposition of states in quantum mechanics. So alpha times 0 plus beta times 1, we'll use the Dirac notations. and it's normalized. So typically you will see that people represent the qubit as a sphere. This is called the Bloch sphere. And the north pole is the state 0, the south pole is a state 1, but then you can get any state in between. And this is claimed to bring some power to quantum computers compared to the classical ones, as we are going to discuss. Now, in order to build a quantum computer, you need to build a quantum register, and this is basically a stack of n qubits. So the state of a quantum register has a Hilbert space, which lives in a Hilbert space which is very big, is the tensor products of C2s for each of the qubits, and the dimension is 2 to the power n. This is sometimes called the curse of dimensionality. This is where the complexity of all the quantum computations is sitting. It's in the size of the Hilbert space, because otherwise it's basically a linear theory. A generic state in the Hilbert space is not a product state. So I cannot simply write it as a product of states, each of them in the different C2s that are in the Hilbert space. And what measures the deviation from being a product state, we call it entanglement. That's one way to view entanglement. There are other ways, as we will discuss, but one way is to say entanglement is a measure of how you deviate from a product state. And it turns out that entanglement is essential for quantum computation, but as I will discuss, too much entanglement is also a problem. A simplest example, the canonical example for entanglement, is the Bell state. The Bell state is a superposition of 0, 0 plus 1, 1. And we can quantify it, we will see later, by entanglement entropies. And as we know, entanglement is very delicate. So it's really a true property of a quantum system. Classical systems tend to decohere it. And one of the huge tasks is how to protect these qubits, the entangled qubits, from the environment. The next part in building a quantum computer is what we call quantum gates. And quantum gates are operations that you need to do on the qubits, on the quantum register. And they are performed by unitary operations as quantum mechanics evolves. And unitary operations are reversible. So that means that quantum computation, unlike classical computation, is a reversible process. So the way to appreciate it is you think that if you try to perform a simple operation like 2 times 3 equals 6 in a quantum computer, it has to be a more complicated operation, because you need to be able to go back from the 6 to the 2 and the 3, because you can also get 6 by 1 times 6. And this is not something that we are used to in classical computation, but quantum computation is reversible. The other property of the quantum computation is that you don't really need to build a very large unitary matrix. You can build it from simple 1-qubit operations and 2-qubit operations, like, for instance, rotations of a qubit plus some entangling gate, like a C0 gate or something like that. And this can form a universal set from which you can build any unitary evolution. You can approximate it systematically, and this is known as Solovay-Kitaev theorem. So I'm going to discuss a very basic architecture of a quantum computer, which is a model that you can also see models for black holes, model for condensed matter systems, etc. And this represents quite accurately the actual computer. So basically what you have in the computer, you have in the beginning a state, which we call it the register at the initial condition. So we can take it like 0 to the power n. Then we have gates operations, and at the end there will be a result which we will discuss. And gate operations, here I took them as 2-qubit gates, and they are basically simple rotations. I'll write the matrix in a second, plus a matrix which is called the control Z. And what it does, it operates as a Z matrix, Z sigma Pauli Z matrix on this qubit, on the lower qubit, if there is one in the upper qubit, and does nothing otherwise. So in simple mathematical terms, or as matrices, the rotation gate that I'm using is just simple rotation, cos theta, sin theta, minus sin theta, cos theta. And the control Z operation is a 4x4 matrix, which is diagonal 1, 1, 1, minus 1. So what is happening here? You start with some initial state, and then you start to operate on it with matrices. But these parameters are random parameters. Here I take them drawn from the uniform distribution between 0 and 2 pi. And those of you that maybe have been looking at classical machine learning, it's the same type of analysis you do there. You need to introduce random parameters, and then you study the system as a function of these random parameters. And they help you to do the certain computations, as we will see. So generically, this gate, which is called the control Z gate, what it does, it entangles the qubits. Because if it was not for this one, there will be no operation. Equation 6 by itself, this matrix says they just rotate the qubits, but they do not entangle them. So no computation could have been done. So without entanglement, you can do nothing with the computer. But once you start to entangle, then there are correlations between the different qubits, and then you can control it and do computations. There is a famous theorem, very simple to prove from the linearity of quantum mechanics, which is called the no-cloning theorem, which tells you that it is impossible to copy a quantum system. There is always a very unique copy of a quantum system. That means that you cannot copy information that exists in qubits. This is something we are not used to in classical computing. In classical computing, we can copy from one part of the program to the other. Here, we cannot do it. Once you try to copy it, you will delete the information in the other qubit. We know that very well from teleportation, and it has dramatic consequences, of course, for cybersecurity, but also for quantum computing. Last is a topic that I'm not going to discuss really today, is noise. Quantum systems are extremely delicate because they can get lots of noise from the environment, but it's not just flipping zeros and one. There could be phase errors and all kinds of other errors that it's a manifold of errors that you have to fix. And you cannot fix it in the ordinary way, because ordinary ways you duplicate the information. Here you cannot do it because you cannot clone. And also you are unable to measure the data qubits because in order to detect the errors, because otherwise you will destroy the information. So all in all, life becomes more complicated, and again, it's entanglement that comes to rescue in order to solve the problem. But some people say that we might never have a quantum computer, but at the end of the day, we know that there is a very big quantum computer. It's the universe, and the universe is just a giant quantum computer. And therefore, we do believe that it is possible, at least in physics-wise, to build it. What are quantum algorithms? So quantum algorithms, in fact, the next 10 years is going to be what is called the NISQ technology. This is quantum computers that are called noisy intermediate scale. And noisy intermediate scale quantum computers means that you are not going to correct noise, you just let them go and see what happens. And therefore, there is a huge challenge now to understand what can you do with them. Many people are thinking about machine learning, optimization, etc. What I would like to understand is, from physics point of view, what is the role of entanglement and chaos in this type of machines? So what is a typical problem for a quantum computer? A typical problem is to find the ground state of a Hamiltonian. Now we know in physics we are always interested in low energy states because they describe much of the physics that we can explore, and that it can be in condensed matter, it can be also, of course, in particle physics, and it is actually a way to encode many quantum optimization problems. So the way it's done is the following: there is a Hamiltonian, but it is called a k-local Hamiltonian because the Hamiltonian is a sum of terms. Each of them acts locally on k qubits. This is something natural in physics because interaction is typically local. So it is unlikely there will be a piece of the Hamiltonian that acts on too many qubits at the same time. So this is a natural assumption. And it turns out that if you can find the ground state of this Hamiltonian, or the Hamiltonian that we devise for the problem, you can solve a large number of problems. And oops, I don't know if you see the last line because I cannot see it, but what happens is that the way you do it with a quantum computer is that you are building a state. A state is basically you initialize the computer by some initial state, which is 0 to the power n. You act on it with some quantum computer, namely some unitary matrix. A quantum computer at the end of the day is just a unitary matrix as a function of many parameters which are random. And then you evaluate your cost function. And you do what we normally do in variational principles. We try to minimize and search for the ground state of the Hamiltonian. Now comes the question, when you try to search for the ground state of the Hamiltonian, what should be the good state of the quantum computer? In which way you should prepare it? And it turns out that entanglement and chaos are important properties of that in order to answer this question. So at the end of the day, what is a quantum computer? From this point of view, it's just a 1 + 1 dimensional system, which is chaotic. We'll see that it's chaotic, but naturally you expect it to be chaotic because it's highly interacting. There is the space direction, which is the direction of the states of the qubits, and there is the time direction, which is the direction where we evolve by these unitary gates. And at the end of the day, we need to study a discrete 1 + 1 dimensional system. So what is a property of quantum systems which is very crucial for the analysis? This is the entanglement. What is entanglement? So typically, the higher the entanglement, it means that we are spreading the information more and more around within the qubits. And in that case, if I try to get any information out, I need to measure a large number of the qubits in order to get that information. And information will be responsible both for the success, but also the failure of the algorithms. And what I will try to do is try to find an optimal regime of information spreading in order to do the analysis, in order to perform good computations. A measure of entanglement is entanglement entropies. This is one measure of entanglement. And typically the way it's done is you take the system of n qubits and you divide it to 2 parts. Let's call it part A and part B. And what you do, you construct a quantity called the reduced density matrix. So this is the reduced density matrix, which is made out of the density matrix of the circuit by tracing over one part of it. And this measures the amount of entanglement between the 2 parts of the system, part A and part B. And you can use the eigenvalues of that matrix in order to build entropies. There are various entropies. These are called the Rényi entropies. A particular limit of the Rényi entropy is so-called the von Neumann entropy. And if you use these entropies, you can evaluate how entangled your state is. So if I take a state of a quantum computer or any physical system, and I would like to know how entangled it is, I can try to evaluate its Rényi entropies and get a measure of the entanglement. And as I said, one way to think about entanglement is how far it is from a product state. So how the different components are entangled with each other. Let me give you a simple example. So we take the Bell state from before, and if we look at the density matrix and evaluate the reduced density matrix, we'll get a simple 2x2 matrix. And if I'll calculate the Rényi entropy, I will get 1. In fact, all the case Rényi entropies will be 1. This is the maximal entanglement that you can have. So this state exhibits the maximal entanglement. And indeed, intuitively, you understand why. Because if I measure 0 on qubit 2, it immediately will tell me the qubit 1 is 0 and the same with 1. So they're really highly entangled. Now, how the entanglement of the quantum computer or typically quantum system evolves with the number of gates that we are in place like that. if you look at the number of layers of the qubit of the computer as a function of the number of qubits, you will see that it always goes like this. There is a ballistic growth, and then after that there is a saturation. The same story is with geometric measure, which is a measure of how far you are from a product state. So the way entanglement actually works, in the beginning, when you start to apply these unitary operations, it entangles very fast. And then there is a fast growth, and after that it stabilizes to a plateau. And in that plateau, the entanglement is already very, very high. So the question for us to ask is, where should we be when we try to use the quantum computer? Should we be in the regime of highly entangled in entropies, or should we be in the regime of lower entanglement? And actually, it's a tricky question, because naively you would think that entanglement is actually a very good resource. Let's use as much entanglement as possible. It turns out it's actually not true. And as I will explain, there is a physical reason for that. By the way, these are numerical simulations. So you can simulate this quantum computer, and we did many of them. And you can see that these plateaus, you can evaluate them for the different entropies, for different number of qubits, etc. You'll always see the generic structure. Analytically, to prove, evaluate the structure of the curve analytically is not a simple task. And the plateau is very close to what we call the maximally mixed state. The maximally mixed state is a state where the reduced density matrix is like the identity matrix. All the entanglement entropies are maximal, and this is a particular limit of the thermal state. Typically, to get to the mixed state, it will take you an exponential time, but to get close to it, you can get it in a polynomial time. And there are other numerical simulations that exhibit what's the differences between the von Neumann entropies and the higher NE entropies, etc. They all show you, and there is a lot of information in this data, but basically, if you just look at the qualitative structure, you will see that, let's say in the quantum computer that I was showing you, this architecture, at around 40 layers, namely 40 layers of qubits, you will reach already the plateau. So that is the question is whether this is fast or not. It depends on the question that you want to answer. You can the entanglement entropies show all kinds of monotonicity properties which you can study, but at the end of the day, you will see that already at 40 layers, all the different entanglements saturate, and they are close to each other. So therefore, for this architecture, what will happen is that all the qubits are going to be almost maximally entangled at that state. And the question is whether this is good or bad. So this brings us a little bit back to question in physics and the qualitative differences between entanglement entropies of quantum states. And we typically distinguish two types of entanglement scalings. Entanglement which is called the volume law entanglement, and entanglement which is called an area law type entanglement. What is the difference between the two? So if you look at a K-local Hamiltonian that has a mass gap, so if you divide the Hilbert space to two parts, part A and let's say part A bar, if there is a mass gap, then the correlations are very short range. You would expect that the qubits that interact are only the ones that are close to the border. So that means that you should get something which is called, the scaling of the entanglement should depend on the boundary of the region and not the region itself, not the volume. This is called an area law. Intuitively, it's clear, but actually to prove it is very difficult. There is basically one proof in one dimension, and in higher dimensions, a little bit of evidence, but not real proof. But typically, that's what you expect. On the other hand, the volume law would mean that all the qubits in region A and all the qubits in region A bar are basically talking with each other. They are correlated. This is a very long correlation, and this is not a property that you think a gapped system has. Now, what happens in our our computer, the region that was linear is a region which is a region of area law. And the region of the plateau is a region of volume law. So now you know the answer to the question I was raising. If you try to search for a ground state of Hamiltonian, which is k-local with a mass gap, it has typically an area law entanglement. So don't try to entangle your computer too much, because then you will be in the volume law regime, you will have a hard time to get there. So that's basically where the physics tells us how much entanglement we should use in the quantum computer. In fact, you can prove a few theorems that I will skip to understand, to quantify exactly what you need to do here. But typically, the answer that you will find is, as I said, if you want to solve problems of k-local Hamiltonians, do it with mass gap, do it in the linear regime. So now there is a little bit of numerics that I will show you. There is much more in the papers. This is the transverse field Ising model, trying to find the ground state of that model. But we did also, as you can see, the long-range Ising model and also the chaotic SYK model, which is different. The difference between them is that nearest neighbor Ising model and long-range Ising model, the ground state satisfies an area law, while SYK model, SYK4 model, has a volume law. And if you look at the entropies of those, you see that it's what I was saying, the maximal entropy for 12 qubits, if you divide to two parts, will be 6, and you see that both the nearest neighbors Ising model and the long range are very far from there. While the SYK model has a much higher entanglement entropy, close to that number 6. So that means that if I try to search for ground states of Ising model or long-range Ising model, both of them I should stay in a linear regime, while SYK model, it's a different one. And indeed, it's true. In the simulations, you can see that this is correct. The way the simulation is done is you prepare the quantum computer, you measure the cost function, and you do what we call gradient descent of search. And what you can see in these plots is that a very small number of layers, the part, let's see, the part here is the number of layers, I mean the horizontal axis, and you see that for until the 40, before I reach the plateau, I can see that the energy difference between the ground state and the computer is close to 0. That means a very good solution. After that, there is a problem, and you see that the entanglement entropy diagnoses that exactly. It knows exactly where to find or how to diagnose where to find the ground state of the Hamiltonian. You can do more than that. One of the tricks that you can do is play with the quantum computer as a random graph and then start to remove entangling gates and ask what happens if I actually start with too much entanglement and I just remove slowly entangling gates, what will happen? And you see the same property that I was discussing before with the probability which is bigger than 0.2 of removing entangling gates, you get very good solutions, or you find the ground states of the Hamiltonians. So again, it just supports the same statement of before. You have to correlate the entanglement entropy of the Hamiltonian, the ground state of the Hamiltonian, to the entanglement entropy of your quantum computer. You can also study the quantum energy landscape, namely the energy function as a function of these random parameters, and ask how it looks. And it turns out that it has a very large, it has a structure of flat directions and a very small variance in the gradients if your entanglement is high. So again, it tells you that it's going to be very hard for you to try to solve the problem if your system is too much entangled. Similarly, you can study the Hessian of that, and that the Hessian of that has the typical structure that when it works well, it has a regime of very large eigenvalues where it can actually find the solutions, So these properties are generic properties, and they are correlated with the entanglement. This is actually structure which is reminiscent of the gradient descent in deep learning. People found the same structure there. Now there is the issue of the number of parameters that I introduce, the number of random parameters that I introduce in the system. Whenever I act with a quantum gate, I introduce random parameters. Is it good to add many parameters, or is it bad to add many parameters? It turns out that it's very similar to over-parameterized deep learning networks. If you put more and more parameters, it actually helps the system. Now, this is counterintuitive for us as physicists. As physicists, if somebody tells you he has 5 pieces of data and he has 100 parameters to describe it, you would think it doesn't make any sense. Actually, it turns out that in machine learning, it makes a lot of sense. The number of parameters is much larger than the number of data points, but actually it has an explanation. This explanation, which has not been worked out analytically to date, but it resembles the large N simplification that we know in field theory. You have many more parameters, space of functions simplifies. Let me spend a few minutes on classical chaos and quantum chaos. So classical chaos, so an integrable system, a classical integrable system is a system that has, let's say, n degrees of freedom, but it will have n conserved quantities that has Poisson bracket 0. They are in involution. And we know that you can solve these classical systems by action eigenvariables. Chaotic systems do not have this property, do not have this number of conserved quantities, and therefore they are sensitive to initial conditions. And we know this famous so-called butterfly effect, where if you have a small change in the initial conditions, they exponentially increase to a separation of trajectories. What happens quantum mechanically? I mean, how classical chaos translates into quantum mechanics, and how chaos appears in these quantum computers? So quantum chaos, actually there is no one definition, but one would try to understand what is the manifestation of chaos in the quantum version of classical chaotic systems. And what we do know about quantum chaos is not one definition, but we know a few diagnostics that tell you whether the system is chaotic or not. Now, there is an interesting story about that. You can look at for instance, the eigenvalues of a Hamiltonian of a chaotic system, but you're not going to see anything interesting. What you see interesting is in the separation between eigenvalues, the eigenvalue differences, or it's called level spacing. If you look at the level spacing distribution, you can see properties that reflect a chaotic system compared to an integrable system. And one of them is the distribution of those eigenvalues, eigenvalue separation. So here S means the separation between two eigenvalues, two nearest neighbor eigenvalues. And if you look at the integrable models, they have a Poisson type distribution, while random matrix theories that are certain universal structures of quantum chaotic systems have a different distributions. There are some called Gaussian orthogonal ensemble, Gaussian unitary ensemble, etc. And the property that they have is that if you take the limit S goes to 0, while here the distribution P of S, so the distribution P of S here will go to 0, while here it's not, and this is called level repulsion. So it's interesting that you see the properties of chaos in the differences in the eigenvalues. Another diagnostic is called operator spreading, which was heavily used recently in the study of gravitational systems. And it basically asks the question, if I take a local operator that commutes with another local operator far away, how long will it take when it evolves to spread so that they will not commute anymore? And this can also be quantified by expanding the operator in terms of a certain basis of matrices, and I'm checking how long will it take it to overlap with the other one. Instead of doing the mathematics, I can show you a picture, a plot. So this is this quantum computer I was discussing before. We put an operator which is localized only on certain qubits in part of the computer, and then we let it evolve in time and see how it spreads. And you see that very quickly, again, it's magic number L equal 40, which is the number of our computer. You see that it was spreading all over. So therefore, the operator spreading actually has certain properties similar to the entanglement, even though it measures a totally different object. So what is the analog of the Hamiltonian and the eigenvalues of the energy eigenvalues of the Hamiltonian of chaotic systems? One way to do it here in the quantum computer is look at the reduced density matrix. And if you look at the reduced density matrix, you can build from it a Hamiltonian. This is called the modular Hamiltonian, and look at the differences in the eigenvalues of that modular Hamiltonian as a function of the number of gates. And you will see the chaotic properties of the quantum computer exactly as a function of this number of layers or number of gates. And the more entangled the quantum computer is, the more chaotic it is. It means the more complicated it is to actually solve the optimization problems or any other problem you'll be interested in. So there are other measures of chaos. One of them is called R statistics, which is you take the minimum of the separation of eigenvalues at level I and level I plus 1, defined like this, and then it turns out that there are characteristic numbers for random matrix models. You can evaluate them also for the quantum computer. And actually you will see that with 12 layers, you are getting close to one of those distributions, while if you will go to more layers, 40 or 50, you will be, in this case, it is the GOE. Other gates will give you GOE. So therefore, the quantum computer develops chaos as a function of the number of layers, and these chaotic properties are basically correlated with entanglement. You can also evaluate the distribution of the eigenvalues and how far it is from the Poisson distribution, and you will see perfect agreement with the random matrix models when the number of layers is around 40 or 50. So basically it tells you that the quantum computer became chaotic. Another diagnostic that has been used heavily recently is called the spectral form factor, which is basically the Fourier transform that tells you, basically measures the separation between eigenvalues, and it has an interesting structure in integrable systems compared to chaotic system, and basically it is called a dip, and there is a dip which is non-universal, and there is a linear ramp. You can also check this for the quantum computer. It does the same thing. You can see that it actually falls in one of the classes of matrix models that we know, random matrix models like GOE, GOE, etc. Again, as a function of the number of layers. So basically, the message is the following. The quantum computer is basically a simple physical system that exhibits two things, entanglement and chaos. And they are correlated with the ability of the quantum computer to calculate. By the way, for us, from point of view of physics, calculation is a simple evolution. Any experiment we do in the lab is basically some kind of a quantum computation. So this basically tells you the limitations of those computations when your system is too entangled or too chaotic. There are many challenges in this field, challenges which are not directly related to us, in order to build algorithms and in order to for those computers, but there are questions that are related to us. How do you use your quantum circuits and study them? And there are all kinds of ideas, from tensor networks, condensed matters, and of course quantum gravity. There is another interesting topic which is emerging, which is the relationship between what we call quantum machine learning and classical machine learning, and the physics of these two. So let me stop here, and thank you for listening.
Thank you very much. So questions, last questions for this long day. So what is the most successful physical realization of the computer? There is, you know, this cold atoms, lasers, and
Right. So this is a great question. So there is a competition in this field, and basically there are three types of schemes. So one of them is the material qubits, as you say, the all kind cold atoms, the superconducting qubits, etc., which seems to be successful in the sense that people manage to build the quantum computers, you know, with several dozens of qubits. The problem is the scaling of this might be difficult because it requires a delicate separation from the environment, and that's hard to get. There is a second version which people are trying, which is based on silicon photonics, and that one, if works, has a great future, except that it has the following two issues: one, a great advantage, and one is disadvantage. It's based on photons. And photons don't interact with the environment, so there is no much noise. So this is great. On the other hand, photons don't like to entangle with each other.
yes.
So it's actually bad. So there is a lot of conservation of difficulty here. But if this works, it will be great. The third one is called topological quantum computing. Topological quantum computing is based on, you know, similar ideas to what we know in our field as topological field theory. And it's basically using the fact that anyons are very clever, and they have a statistics which is different than statistics of bosons and fermions. And you can use braiding groups or braiding operations in order to construct the quantum gates. So this one, by the way, experimentally is lagging behind the two others. It's hard to know, but probably by 2030, we will have a reasonably good quantum computer. That's actually what we are being promised. And then we'll see what we can do with it.
Okay, thank you very much. There is one more question. Okay, go ahead.
Hi. So you mentioned several times that in actual quantum computation, you have to do iterations of these gates and then measurements. So measurements presumably being this non-unitary thing. How should I imagine in an actual quantum computer, how do they do these measurements? I have no idea. Can you briefly give me an idea? What is being measured?
Yeah, it's actually the same measurements you would do in the lab, right? You measure the values of the qubits. I mean, there is a state in the beginning and there is a state at the end, and you can depending on, I mean, for instance, you can, or the observable, right? You can measure the energy, and then by that thing, what we will happen is a collapse, right? Because you will your state will be destroyed and you will get something. You have to repeat it many times in order to get state homography, and there is a question in the field, which is how long does this take, or how many resources it takes. People expect it to be polynomial, but you know, for instance, there are many places that you can lose the exponential power of the quantum computer if these steps of measurement, and also in the beginning, the initializations, will be too costly. It is clear that it can give an exponential advantage, but you can lose it in various places. So this is one of the places that if you are not smart enough, you might lose it, even though there are already papers that try to argue that you can do that, polynomially.
Thank you very much for a nice talk. Okay. So
thank you very much
for participating.
Okay.
Be patient and stay in Sunday. Today's Sunday, right?
Right, today's Sunday.
Okay, thank you very much. I love you.
Okay, thank you. Bye-bye.
It's your Savidi, by the way. Okay. So, bye-bye.